Hi, everyone. Welcome and good afternoon. My name is Benjamin Quinn. On behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm so excited to introduce this virtual event with Alain Bécoulet, presenting his book, Star Power, ITER and the International Quest for Fusion Energy, in conversation with Nathaniel Fisch. I hope you're all well and safe. Thank you for joining us virtually. This afternoon's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. Although summer is here, we do have a few more events in the works for the remainder of the summer before kicking off one of our busiest fall seasons. To learn more about this and our other upcoming virtual events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more info. I'll also be posting a link to our Science Research Public Lectures channel in the chat, where you can view previous talks you might have missed. This afternoon's discussion will conclude with some time for your questions. If you have a question for our authors at any time during the talk today, click on the Q&A button at the bottom of the screen and we'll get through as many as time allows. In the chat, I'll be posting a link to purchase Star Power on harvard.com. Your purchases and financial contributions make events like today's possible and help ensure the future of a landmark independent bookstore. Thank you to our partners at Harvard University, and thank you all for showing up and tuning in support of authors, publishers, indie bookselling, and especially for science. Now it is my pleasure to introduce today's speakers. Alain Bécoulet is head of engineering for ITER, an international nuclear fusion research and engineering demonstration project in France. Previously, he was director of the French Magnetic Fusion Research Institute. He was awarded with the 2020 International Science and Technology Cooperation Award of China and the 2021 Huangshan Friendship Award of Anhui Province. Today, he is joined in conversation by Dr. Nathaniel Fisch, professor of astrophysical sciences in the Department of Astrophysical Sciences and director of the program in plasma physics at Princeton University. For his work, he has received a Guggenheim Fellowship and is a fellow of the American Physical Society and the NASA Institute for Advanced Concepts. This afternoon, Alain and Nathaniel have joined us for a discussion of the book Star Power, a concise and accessible primer on fusion energy and its role in a greener future, which Bernard Bigot, Director General of ITER, calls a welcome overview of the role of hydrogen fusion in our transition to a zero carbon emission world. Making this topic accessible to all is no small feat, but Alain Bécoulet has done just that. I will end with the final praise from Anne White, professor of nuclear science and engineering at MIT, who calls Star Power a truly unique perspective on the challenges and promises of fusion energy. This book belongs on the shelf of anyone looking to navigate the rapidly evolving research pushing nuclear fusion onto the grid. We've got a lot to learn this afternoon, so without further ado, I am delighted to turn things over to our speakers. The digital podium is all yours, Alain and Nathaniel.
Thank you, Benjamin. Good afternoon, everyone. I mean, it's my real pleasure to be here with you. I want to thank warmly Harvard Bookstore for this invitation. It's a real pleasure to be here with you and try to discuss not only my book, but really the progress and the development of fusion energy and of the ITER project. And I'm also delighted to have my good friend Nat Fisch with us today, and we hope we'll do a good discussion around this book. First of all, I propose to have a short introduction, a short meaning something like 10-15 minutes on the ITER project and fusion, so that you all have a global picture of what is the project and what you will find in the book, and then we'll go for a conversation and for Q&A. I'll try to share my screen. Hopefully this has worked in the previous attempt. So I need to know if all of you now see my screen. I need a confirmation by Nat or whoever.
It's good.
It's okay? Okay,
yeah.
Very good. So, I will introduce, as I said, this topic, and essentially the ITER project, which is a sort of, let's say, bottleneck, or at least very important milestone on the path to master the fusion energy. The question is very burning these days, and I can tell you that today in France it's 41 degrees in the place where I'm living, so it's really an issue. It's very important for the mankind and for the planet to get progressively but rapidly rid of the carbon energies, so the fossil energies, and to go to carbon-free production of energy. For this, we have only two solutions, essentially, the renewables and the nuclear energy. The renewables, very rapidly, we all know that they are very attractive, they are developing, they are very promising, but they are still have to face their intermittency on the one hand, and the fact that in any case, they are low density production of energy. And concerning nuclear energy, today nuclear fission works, but and is available, but has nevertheless its acceptability problem in terms of safety and of management and of the high activity long life waste. And hydrogen fusion, if we manage to master it, will basically address the two drawbacks of the two previous ones. Namely, having very high energy production with no very low problem of safety and waste management, and no problem of intermittency or density of production. The challenge is, of course, that we don't master it yet, so we must demonstrate the mastering. And the mission of ITER, the project that I will try to develop today rapidly, is essentially to demonstrate that we can master this in an industrial way. So what are we talking about? We are talking about trying to put the sun in a box, so trying to reproduce and master and use basically the nuclear fusion reactions that take place in the universe, in the stars, in our sun, in basically almost everywhere in the universe. But today we cannot reproduce this on Earth. This is a mechanism that was suspected and then modeled and developed and understood already for more than 100 years. And only by the end of the 1950s or 1960s, we started to imagine that we could really domesticate this kind of energy and create a source of energy out of these reactions. The big challenge, of course, is to make a box, is to have a box that can contain a small part of the sun and then use it as a source of energy. For this, we have two channels for fusion reactions. One that I will not detail here, which is called the inertial fusion, and one that is called the magnetic fusion, magnetic confinement fusion. This is the one I will detail. So basically, this box is a magnetic cage called the tokamak. The challenge is to build such a box, is to trigger those reactions and then to master them for a long time. So essentially, fusion on Earth means that we need to take a mixture of small nuclei, essentially deuterium and tritium, the two isotopes of hydrogen. And if we manage to have them colliding at sufficiently high speed, they will, of course, break, or they will overcome the Coulomb repulsion. And then they will fuse, they will go to a nuclear reaction, triggering a helium nuclei and a neutron and energy. All this takes place basically in a mixture of deuterium and tritium that we have to bring to 100 to 150 million degrees. So this is the challenge, and I will come back on that. What you see immediately in these this reaction, is the fact that, first of all, it's not a chain reaction. The neutron is not used to continue the fusion reaction. So it's not a reaction that can lead to a loss of control and to a divergence. Second of the important point to mention here is that the fact that the fusion products are neutron and helium, so there is nothing like a high activity or long life nuclear waste triggered by this reaction. The challenge is still an important one, is the fact that the tritium, the deuterium nuclei are very abundant, the deuterium atoms are very abundant on Earth, so we have no problem with this. But of course, the tritium atom is a radioactive nuclei with a very short lifetime, something like 12 years. So it doesn't exist naturally on Earth. So we have to create it. In a machine like ITER, we will import tritium from outside, but in a nuclear reactor, the idea is to create the tritium in situ, to burn it, and then so to manipulate, finally to have the only radioactive element will be created and burned locally. How we do that? We will use the neutron that is created by the fusion reaction. This neutron will escape naturally the confinement zone and hit locally outside of the plasma, will hit lithium, will hit a blanket that is enriched with lithium and will make fission reaction with lithium, creating the tritium. So essentially, the elements that we will burn in this kind of reactors will be deuterium and lithium and create energy out of this. What is quite important to understand here is that 1 gram of deuterium tritium is equivalent to burning 8 tons of oil. So we are on a very, very powerful process. Rapidly here, the story of ITER is already long. So as I said, in the 50s, we decided to investigate this kind of situation, medium machine. It took a couple of tens of years in order to study this kind of confinement, magnetic confinement. In the middle of the 1985, there was an important political event, which was the summit between Reagan and Gorbachev in Geneva, trying to reconcile East and West, and they decided to have a flagship of this reconciliation, and fusion was this flagship. And in a sense, they created the idea that we could all together build a fusion machine. It took something like 21 years, so the political times are also very long in this story. It took something like 21 years in order to gather the correct partners and to find the fundings and to find the location for such a project that was named ITER. So today, China, EU, India, Japan, Korea, Russia, and the US are working together. This represents half of the world population. In order to create such a machine and to create such a demonstration of the fusion reaction. The machine was located in France, in Cadarache. That's the reason why you see the French president in the middle of this meeting, and the fact that this agreement took place in Paris. 15 years later, ITER appeared last year at the COP26. So ITER appeared also on the map of the possible energies that are now to be envisaged for the long-term transition of energy transition or energy mix transitions. I take the opportunity here to point out that this was carried out by our previous Director General, Bernard Bigot, that was mentioned in the introduction here. Unfortunately, Bernard Bigot died in May this year from a long disease, and we really miss him now in this project. He was really the soul of this project. So the mission, as I said, is to find a box. You will see that this box is called a tokamak. It's a magnetic trap that has this very specific shape of a donut. This donut, it's a plasma donut in a sense, which is brought to this 150 million degrees. The mission of ITER is to demonstrate fully the integrated scientific and technological feasibility of fusion. The goal that, or the target that is given to ITER is to create 500 megawatts of fusion power out of 50 megawatts of heating power. You understood rapidly that it's an amplifier of power. You heat the medium, and then the medium starts fusing and gives you more power. I draw your attention, I will come back on that, on the scale of this device. You see here somebody not sitting, but staying inside this machine. So it's a very large reactor. As I said, it's a worldwide partnership. So for the past 60, 70 years, all these members, all these countries, all these partners have worked together, and they are still working together. You see here the sort of galaxy of fusion machines that are still under operation around the world and that are continuing to contribute to the consolidation of the construction of ITER. So it's a very important network and very collaborative one. If I take a picture of the site itself, you see that ITER site is a full plant. Well, one of the missions is really to demonstrate that not only we can create this energy, but we can master it also, and we can essentially manage the whole cycle, also the fuel cycle itself. So we can manage the whole story, the whole nuclear aspect, etc. This is the first, it's really a first of a kind, and it will be a sort of go-no-go for this way of working. So it's an important point. I have no real time. We can come back on the questions on developing the details. The machine itself, as I said, is a tokamak. It's a very large one, and essentially it's a very large magnet. It's an immense magnet. So it's a magnetic trap that is created by a number of coils. You see, I have no time to detail this. And this very large magnet is very heavy. As it is built in France, we count this in a number of Eiffel towers. So you see that the weight of this device is quite large and difficult to manage. And I end up this presentation with a couple of actual pictures, photos. So this machine is today under assembly, under construction. And you see examples of the various parts that are provided in kind by our members. You see elements of the vacuum vessel sector. So this donut that is cut in 9 parts. Some of them are built in Europe. Some of them are built in Korea. You see magnetic field coils. So the various elements of the coils that are built or manufactured in Japan, in Europe, in Russia as well. You see the elements of the cryostat that is built by India. The element of the central solenoid, it's the central part of the magnet that is built and delivered by US, or that of the connections to bring all this power and cold liquid helium to those magnets that we call the feeders. They are manufactured in China. Of course, we are in Cadarache. Cadarache is not on the seaside. It's something like 80 kilometers recessed from the seaside. So all these elements are brought by boat to the harbor of Marseille, and then they are moved by exceptional transportations and exceptional convoys on the road. We already have on site 14 of the 18 coils, etc., etc. To deliver. These are basically these exceptional convoys. There are 250 of them expected for along the life of the assembly of the machine. A glance, a look inside the assembly hall. You see the machine is sitting behind this white wall over there, and what you see in the first part of the picture is the assembly hall, where we prepare all the elements and then move them using the cranes down to a pit where the machine is partly assembled. You see here the moment when we have moved the bottom part of the cryostat. You see inside the pit pictures that display the first coils that were installed last year. And as an important milestone here, in May this year, the moment when we lowered down the first the first sector of the 9 sectors that will be progressively lowered down in this pit, welded and form progressively the toroidal chamber. The timeline that we are having at the moment is continuing this first assembly down toward the end of 25 or so for what we call the first plasma, or when the machine is closed and working. And then later on, a series of sub-assembly phases where we complement this machine with the necessary diagnostics, additional heating systems, etc., up to the moment when by 2035 or so, we are the machine is fully capable of creating those 500 megawatt of fusion power. There is a footnote here that is important. As you may imagine, the last 2 years and the COVID pandemic has impacted us and is inducing some delays that we are accounting for at the moment. After that, what's the point? After that, we think we have the demonstration and the full plant demonstration that we can master this fusion energy. So the door is open for the next step devices, and in particular for energy and electricity productions. This is a generic so-called program, so-called demo, with different solutions, different possibility depending on the members. And if I go here on the sort of timeline, if ITER provides its outcome between 2035 and 2040, we can imagine that in the 50s, 60s, we are able to build and to couple to the network such kind of power reactors. One last word, because it's very important. All what I showed you here represents public investment, public involvement in nuclear fusion. Since the moment when ITER was decided, there has been a lot of interest developed by the private industry, by the private companies and investors. And now we see a large amount of companies that are trying to catch up, that are trying to help, that are trying to innovate on what ITER is building up at the moment. And there is a lot of very interesting adventures. This is a sort of temporary map, just recognizing that US is really ahead of all the others on this. And this is a very important movement that will certainly help accelerating the path to actual fusion energy production. And so thank you very much. I hope I was short enough, but detailed enough so that we can initiate a discussion. Thank you so much.
Alain, that was terrific, and it encapsulated what's in your book, which is really describing a fantastic piece of technology and an incredible journey. I'm looking forward to this conversation, but first I just want to thank Harvard Bookstore for bringing us together to have this conversation. I think it's been a couple of years since we've been able to sit in a room and chat, and at least now thanks to Harvard Bookstore, we're able to do this in this virtual room, and it's just such a pleasure. It was such a pleasure to read your book, and it's such a pleasure to see you and just to chat with you.
Thank you.
And let's see, and congratulations on your book. I can only imagine that you're such a busy person. How is it that you found the time to write this book?
The time was taken out of my holiday time for sure, as you can imagine. But it was a pleasure. The anecdote on the way this book was born is an amazing one. I mean, I was giving, as I really used to do very often, a conference. It was in Paris on fusion. I was invited by the Palais de la Découverte, the Discovery Palace in Paris. And I gave this talk, and it turned out that in the audience, there was one good friend of mine that I didn't see for years. And this good friend of mine, it turns out that he's a famous opera singer, but this is not the point. But his father is really a famous pedopsychiatrist, and he wrote, I don't know, tens of books on pedopsychiatry. And he is now a co-editor of the Odile Jacob editor in France. And then when my friend reported to his father this conference, his father immediately said, but we have to have a book. He has to write a book. This doesn't exist. The sort of a book summarizing the things accessible to everybody. That was the challenge. Not accessible to scientists or to technologists, but really accessible to the maximum audience, to the largest audience. So I started, of course, by friendship, I would say, I started to imagine this. I started to draft the book. And there was a very interesting moment when I interacted with this guy who was really challenging me. I don't understand, this is too complicated, get out of here, etc., etc. And that was an interesting moment of education, and it was a very nice time. And so it turned out that then they accepted the book, and that's it. I also must say that the translation by MIT Press, and in particular, I really want to thank Eric Butler, who was the translator here. He did a wonderful job. He didn't take the translation word by word. I mean, he really recreated the book out of what I wrote. That was also a very interesting moment of exchanges with Eric. That was a very, very good moment.
Yes, I was, as I was reading the book, I was thinking that in some cases the translation seemed almost lyrical. I mean, in other words, just the choice of words, well, gave the translation, what shall I say, that certain je ne sais quoi. I mean, it just was cute and made for delightful reading. I was imagining that there was a story behind what prompted you to write the book, because it is a significant undertaking, and it's also such an important thing to do now, to engage the public on what promises to be a spectacular and also very expensive um, undertaking that really involves many nations of the world getting together on this. And I was curious also about the voice that you had in this matter. In other words, you're an observer, you're a participant, you're a historian, you're also a prophet. I mean, you're in the game, and did that make it more difficult for you to write the book, because you come from so many different vantage points?
Sure. I mean, you always wonder, I mean, in this simplification and in a sense rewriting of everything, you always have this debate, internal debate. I mean, it's too simple, it's wrong, what I'm writing is wrong, it's too simplified, etc. So yeah, there has been a lot of internal debates. I had to abandon a number of details. I had to simplify. I had to, if you read the book, to go more often to my kitchen and imagine that I'm boiling water or something, just to give images to people. Of course, I mean, and you are better placed than anybody else not here. You know that this is oversimplified. And up to the point that it might be scientifically wrong, but at least the picture is there. So I had a hard time making it simple. That's very clear.
I think that by the time I finished your book, I had a very good idea of what you had in your kitchen.
I must tell the people that I love cooking.
Yes, right. And I thought that that was delightful, because it was just nice to see all the similes that you introduced to just explain physical processes and make them more accessible. Like I said, it's just so important to engage the public, and this book goes a long way to doing that. I was I you went through the the technology of ITER very quickly. I mean, you only had a few minutes. You just wanted to give an overview. It's just such fantastic technology. I was wondering if I could just show a few pictures, and maybe you could just, tell the audience over here just a little bit of the story, a little bit more of the story behind this. Let me see if I can share my screen on this, and just ask you for just a few things. Just only have a few slides here. Let's see. So I think that this is some diagram of ITER. I think that you see this now. On the right, you see a little person in the right hand corner. It just gives a feel for the scale of what this is, and this is just the center part of ITER, and there's so much auxiliary equipment that has to be connected to it. Maybe you can just point out some of the key parts of this, like maybe what's in yellow on the right. Yeah.
So maybe at the same time you can help me with your mouse, because I don't think mine will be seen. But
okay.
So
right.
you see this toroidal part, vacuum part in the center is really the place where the plasma will sit, and it is the place, of course, where the magnetic field is established and is capturing, is confining the plasma, because there is no material medium that can confine 150 million degree medium.
Yeah, and so, this
is what you see in yellowish green around is what we call the first wall. This first wall is essentially the moment when the plasma, this very hot plasma, is a sort of thermos bottle, is a sort of insulator, very strong insulator. And at the edge of this plasma, of course, the temperature goes down and meets eventually the wall. So this first wall is there to take a part of this of the flow of the energy that's, or the power of the heat that is flowing out of the plasma. So everything in yellowish or greenish here is actively cooled. Of course, the water is flowing everywhere, and this is where we will capture the power. We will capture the heat, and then, of course, evacuate this heat outside, eventually creating vapor and electricity out of it. The bottom part of this first wall, this kind of W-shaped brownish part, is called the divertor. This is a place where, in fact, thanks to the configuration, the detailed configuration that we are creating here, it's in fact the place where most of the power is evacuated. You have to realize that this green, brownish part, no, it's a little bit above that, the divertor itself. It's made out of massive tungsten that is also actively cooled. And this part is taking the maximum of the heat flux. This maximum of the heat flux is of the order of 10 to 20 megawatts per square meter. If you were to land on the sun, you would basically face this kind of heat fluxes, 2 or 3 times more, not more. So you have to understand that the first challenges of this kind of technology is to create this kind of elements, this kind of systems that are able essentially to land on the sun. But if you just get a little bit out of this plasma facing components, this first wall, you find the first coils, the toroidal field coils, or these D-shaped bluish or bluish D-shaped elements. These are magnetic field coils. You all have to realize that in those coils, for the reasons that we want them to be superconducting, in those coils, the temperature is 4 Kelvin. The temperature is minus 269 degrees C. So essentially, in something like less than 2 meters, you have a gradient of temperature between the core of the plasma, where you have 150 million degrees, to the first coils here, where the temperature is 0, essentially, is 4 Kelvin. So we have to create this kind of system, this kind of box, where we are able to cope with a temperature gradient of this kind. So 150 million degrees difference on less than 2 to 3 meters. This is, in a sense, not existing anywhere on Earth. So, as I mentioned during some of the picture, you see also, for instance, this very big central gray column, which is called the central solenoid. This is the place where, by changing the flux rapidly in this, by changing, sorry, the current rapidly in this coil, we create an electric field in the plasma, and we create some plasma current that helps doing the configuration, but also heating the plasma, etc., etc. You see some of these sort of pipes, several colors that are getting out or in, are the feeders, are all these big items that are bringing the current and the helium from outside to inside, knowing that the whole box, the whole machine is embedded in a cryostat, this huge cylinder. The cryostat is another insulator in a sense. All the internal part of the insulator is at very low temperature, and the external part, of course, is at low temperature. So it's a huge machine that is there to create a magnetic field, but that also to cope with all the constraints that the plasma will then create.
So let's see, you're mentioning that there's 50 megawatts of heating power in this device.
Alors, the heating power is coming from the horizontal square boxes that you see here, what we call the ports. And the additional heating system is twofold. We have 2 ways to heat such a plasma. And essentially, back to my favorite kitchen, either you imagine that the plasma is a sort of cold water in which you want to put hot water, so you accelerate ions at higher energy, individual energy, than the individual energy of the plasma nuclei itself by particle accelerators. This is called neutral beam injection. So we have systems that are injecting something like 16 megaamp, 1 megavolt units. We have several of them. So this is the first element. So you create very fast ions that are injected into the plasma and that bring or transfer their energy by collision to the plasma. And you have the second system, which is basically what happens in a microwave oven. You couple energy through launching waves from the outside of the plasma, coupling the waves to the plasma, and making sure that somebody in the plasma is resonating with these waves. It could be the ions, could be the electrons. So you have several ways of doing that. And then you transfer the energy of the wave to a subset of the plasma, to certain categories of particles. And then again, by collision, they retransfer this energy to the rest of the plasma. So these additional systems are very important. Yes?
So when you do this, you get a multiplication of hopefully 50 megawatts in and 500 megawatts out. How much power does it take to maintain the magnetic field or other systems?
This is I just slightly changed the question, Nat, if you want. Here, we effectively are discussing what we call an amplification factor of 10 between the power we give to the plasma and the power that the plasma is giving back. So it's a pure physical, scientific amplification factor seen from the plasma point of view. But of course, I told you that we are trying to turn this into a reactor, into a production of energy, production of electricity or whatever. So when we go from this kind of device to the reactor, an amplification of factor by the plasma of 10 is not sufficient enough, because it will give, if you include all the efficiencies of the various systems, the fact that you need power to energize or to cool down the magnets and energize them, the fact that a heating system has, of course, its own efficiency, etc., etc. The plug-to-plug efficiency of such a machine like ITER would be, I don't know, 2 to 3, not more. But at the same time, ITER has no goal to create electricity. So if we go to the reactor, we will have to make it a little bit more powerful, a little bit more amplifier than ITER, maybe an amplification factor of 30, 40, so that the overall plug-to-plug efficiency becomes something that is attractive for the energy distribution and energy production. Oh, okay. The good point is that going from 10 to 30 or 40 doesn't mean such a large increase in the volume. So it's accessible, or means maybe more magnetic field or different technologies. We may want to discuss this in particular with the private initiatives that are under development at the moment.
Right. Yeah. Good. I'm just going to flash a few other pictures. So this is the site. And maybe you can point out, this is I guess from a few years ago. This is just to give a feel for how big it is.
So where are we and what is what?
Here's the tokamak here.
Yeah. So if you look on the right-hand side, you have this long and curved building. This is the headquarters. These are the offices. This is where I'm talking you from. The right-hand side, the curved, the long building here. Okay, you see it on the right.
Let's see. Oh, this one here.
I don't see your mouse anymore.
No. Oh, you don't see where I'm putting my.
No.
Let's see if I can make my.
Yes.
Thing. Well, let's see. So it would.
Okay, this long building on the right-hand side of the picture. Okay. Yes.
Yeah. Right. Okay.
So now we cross the fence. You see a fence. It is the nuclear plant itself. Yeah. So we cross the fence and we go on the work site. on the bottom part of this,
Okay.
you see this 10 fan big factory here, these black things with 10
Oh, yes.
towers.
Right. Yeah.
This is the active cooling system. So as I say, we create energy. So today we don't use this energy to generate vapor and electricity. We just sort of cool it down, but in CW, in steady state. So this plant is a 1.2 gigawatt heat exchanger that allows to deal with all the power that will be generated and used in ITER. So it allows ITER to work steady stately. If I move upwards, you see this very large central brilliant building. This is the building where on the left-hand side, you have the assembly hall. And I brought you inside this assembly hall a couple of minutes ago. And on the right-hand side, it is the nuclear building where the machine is. So the machine is exactly under your arrow at the moment.
Okay. Okay, so that's kind of in the middle there.
This is the central nuclear building. This is really the place where you see this. It has some wings here, and you see this is not finished to build. I mean, it's a heavy, really heavy concrete building. Okay.
Right. Yes. Let's see. So, and then so it's inside this building that we see a piece of the tokamak here.
Yeah. So if you go again, if you move upwards here, you see behind this big. Okay. I want to come back. So yeah, so we are in. Yeah, so we are in this pit here. So this is inside the nuclear building, and what you see is essentially what we have almost now at the moment, at least since the month of May. So you see that the central, this very, very big element that is our pride in a sense, is 1/9 of the vacuum vessel, but equipped already with two magnetic field coils, two vertical magnetic field coils. We have 9 sectors and 18 coils, and we are pre-assembling 1 sector and 2 coils, and then move this in the pit, and one by one, and then we will weld one to each other later on. Today, at the moment, you see that this very big piece of vacuum vessel is shouldered, is sitting, or is lying on a central column, this white big column here. This is not the central solenoid. This is the place where the central solenoid will sit at the very end. But for the time being, it's just a tool that is holding the system, holding the structure, during the moment we pre-assemble and we progressively weld one by one the elements.
Okay.
At the end of the day, this central column will move up and it will be replaced by the central solenoid.
I mean, this is just fantastic technology. Maybe I'll skip over this because maybe there's some other things to get to over here.
No, this is we are back in time here. We're back in time 6 or 7 years ago.
Yeah.
It's the pit, but before the building was built, and it's where it lies.
Yeah.
Yeah. This is also something that is interesting. So we are in the sorry.
Oh, should I go back? Yeah.
Maybe yes. Just 1 second.
Yeah.
It's the place. This white gray things is in fact an assembly tool. So we are in the assembly hall. The machine is behind this picture. And you see that we have two of them. We have 2 systems. They are big scissors. So we take one vacuum vessel sector. We put 2 coils on each side, and then we move them, and we append those 2 coils onto one sector. Then it is aligned, etc., and then move to the pit. What you have to understand is that each of those 9th part of the machine, the weight of them is something like 1,400 tons. It is the equivalent of 4 Boeing 747 at the taking off. So it's extremely heavy, and it's very big. And at the same time, we need to have an alignment. We call for a tolerance that each and every part of this element is aligned to better than to the millimeter. This is a requirement for the system to be perfectly aligned, and for at the end of the day, for the magnetic field to be perfectly symmetric.
Yes, right. Amazing. And let's see, maybe you can say what this thing on the left is?
Yeah, so on the left-hand side, what you have is one of the beam source. I was mentioning the ion, ion acceleration of ions in order to heat the plasma. What you see here is one of the beam sources. And the trick is very interesting here. So each of those holes is in fact a beamlet, and then the beam will be accelerated later on. So this is the moment when we are extracting the ions from the beam. What is interesting is that if you want to be hotter, faster than the plasma, you have to have ions that are above this 150 million degrees or something. So you have to accelerate ions, in particular here up to 1 MeV. And if you want to do that efficiently, in fact, you have to have negative ions. So initially, you take hydrogen, you create negative hydrogen. So you add up to hydrogen atom 1 electron. Then you accelerate those ions. And then after that, they enter into a neutralization chamber where they become again nuclear atoms, accelerated atoms, and then they can enter into the plasma. The challenge is that if you want to create such kind of fluxes of atoms, such kinds of currents of negative atoms at this kind of voltages, at this kind of acceleration, the challenge is extremely large in terms of withstanding all the arcs, etc. So again, you have to have a system that is perfectly clean, where the vacuum is perfectly well controlled, etc., etc. We have a development ongoing. It is in Padova in Italy, where we are prototyping all this before manufacturing them for ITER. Such. It's a big challenge here. On the right-hand side, this is one of the, let's say, one of the poloidal field coils, probably the smallest one, and probably I don't know if it's the Russian one, the one that is built in Russia or the one that was built in China. I'm not so sure here. And it is in a box at the moment where it is tested for again for vacuum and for resistivity measurements, etc.
So let's see. So Alain, I'd like to get to one or two more topics with you, and then there's also a couple of questions I see already in the Q&A. And so I'm gonna stop share on this, and maybe you would, let's see, did I stop share on this? Yes, okay. And maybe in the process we'll answer some of the questions. So one thing that I'd like to, one of the elephants in the room, and in fact that's been accelerating, and you alluded to it here too, is the advent of private capital into the field. And the preface to your book was written by Dennis Wyatt, who is very much involved in Commonwealth fusion systems. And you, in your book, you strike what shall I say, a cautious note, but an optimistic note at the same time, sort of balanced between heralding all of the innovation in the field and the optimism in the field, at the same time explaining that we've been down this road before and it's a long and hard road. So that's not an exact quote, but I think it's close to one. Maybe you would like to elaborate on that, maybe in particularly since even in the last year, actually, I think it was on the ITER site that it was pointed out that there's been like $2.8 billion in private capital in the last year and $2 billion in the last decade coming into the field. Can you say what the role ITER has in this changing world?
I think the first role that ITER had was in 2007 or something, when we signed down the agreement and we started really to make this dream a project. It was the first time when fusion was dated rather than timed. It's not as I showed. I mean, there was a time for the first plasma, a time for the fusion plasma, etc., and not simply fusion will be there in 50 years, and we have said that for the past 50 years. This triggered the sort of consciousness around the world that, okay, maybe this is a solution. It starts to be something feasible. It starts to be accessible. And as I said, despite or besides the fact that a lot of people were working and are working on ITER and this path, the private investor, the private company started to wonder what we can do with it. And there was, for me, there was two kind of answers that we saw in time. It started basically in 2007 or 8. The first movement was to say, okay, guys, this is a cathedral. This is too large, too big. This is too complex. This is too long. You are stupid, sorry, or you are not clever enough. We can do it faster, cheaper. And believe me, in 5 years, you'll find a fusion energy in all your plugs everywhere. So far, I'm sorry, we didn't see anything out of this. You have to understand also that it's a game that those people have to play. But the second stage of the private investment, which is way more interesting and important for me, seen from my seat here, is all this initiative that we see with CFS, that we see with CCFE in UK, etc. We have a number of those private-public endeavors where some people say maybe we can be more clever, maybe we can be faster, but building on what has been already prototyped or defined and investigated. And it is true. When I'm a bit uneasy, when I show demo out after ITER, it is the picture we had in mind, or we have in mind with the existing technologies and existing solutions that we had 20 years ago when we started ITER. But there has been a lot of progress. Just take CFS. I mean, this incredible progress and achievements that they are showing now with how to make coils out of high temperature superconductors, which was not accessible 2 years ago, okay? And which is a promise for having higher magnetic field. And you know that, we have no time to demonstrate that higher magnetic field means more performance or smaller machine, etc. But if you go to smaller machine, you have also to develop other technologies for the plasma-facing components, blah, blah, blah. So it's already a movement for optimization. And I'm very optimistic. I want to see this also as an acceleration movement. The problem is not ITER. The problem is, when does fusion play a role in the energy mix? And we have a real big pressure from the society to provide this solution. So ITER is trapped in this movement. ITER is an important element, and I hope I convinced you, because we are developing a lot of things. We are integrating the things. We are addressing the nuclear aspects. We are addressing I didn't have time, the maintenance, the dismantling, the waste management, all this is in ITER. But at the same time, it's not fast enough. We need fusion, or at least we need to demonstrate if we can master fusion faster than that. So if we are clever enough, if we have what I call a new deal between the private and the public sector, and really that we align all the efforts towards fusion energy, I think we can make it. And it is indispensable. All these people are indispensable for me to accelerate the path to fusion.
Yeah, now it kind of, when you talk about the private-public partnership, it reminds me of the Reagan-Gorbachev meeting that you talked about in 1986, where it was decided that there was going to be important international partnerships. And one of the challenges within ITER was to make that work, and it was an experiment in and of itself, as you describe in your book, which was fascinating. I really like seeing that the way your your worldview of the world events that shaped where we are today came to bear on a scientific problem. The politics and the science were so intertwined. Do you see something like, well, I guess one question is, um, is do you see the same political conditions that started things off with Reagan Gorbachev now continuing with Biden Putin, or or are we going to enter a new age where the partnerships are really going to be public, single country partnerships, but maybe with private companies?
Okay, the present, yeah, it's a bit paradoxical, but the present situation and tension between, let's say, Russia and the rest of the world, I would say, is effectively challenging this model. But what we see today is that the adventure on ITER and on fusion today has not been impacted by this, only by the logistic problems because the borders, because blah, blah, the transportation. But today, both Russia on the one hand and the other partners have confirmed the fact that they continue and want to work together on this. And for you and I, we have been working on this for 30 years or more. I mean, this is also one reason why I'm really dedicated to this research. It's the clear demonstration that there are other ways to interact with people. Okay, that science is one of the main motor to have people working close together to understand each other and so on. ITER is a wonderful place. I mean, you can hear all the languages. It's a Babel Tower on the right and in the nice part of it. I mean, it's a very nice human adventure. And we are every day demonstrating that, yes, we can have a different way of interacting with people. So I hope, and we are all working for that, that of course, what's going on today will not have ITER been affected or too strongly affected. Your question on the private-public partnership is a bit different. If and when ITER has demonstrated this common good, it's a common good for everyone who wants to take the information, the knowledge out of this and do a reactor like this, like that, and so on, will be allowed, will be entitled to do that. And very likely, I also think that who will work with a private-public partnership will have more advantage than who will keep it as a pure institutional development. But that's my feeling. So it's as I said, I mean, it's a matter of having everybody working together and converging to something here. So I'm very optimistic here because we need some acceleration. We need some stronger support because of the situation in a sense.
I'm going to read one or two questions from the
yes.
Q&A, which actually touch on your answer here. Maybe you've already answered it already, but there is a attendee who asks, how is the technology used by ITER similar or different from those used by private companies, such as the superconducting technology used by Commonwealth fusion systems? I think you answered that in your book.
Yeah, I answered this. I think basically it's an evolution, and it's a really welcome evolution. It's the kind of super magnetic confinement or more efficient. By the way, we were discussing the efficiency of the device, the global efficiency. If we go to higher temperature superconductor, we gain on the power that you need to cool down the system and to operate the system, and you gain on the magnetic field. So it's a major advantage if we manage to have technologies that bring us to the 20 Tesla or so rather than to the 5 or 6 Tesla. It's a major advantage. Yes.
There's another question, which I think you touched on as well, and it says, Science magazine story from a month ago, out of gas, talks about a shortage of tritium fuel and claims that there isn't enough tritium for any future commercial enterprise. You won't be able to turn on the reactor even if breeding works as planned. Is ITER just a very expensive scientific experiment?
So yeah, I think I touched it, but I can repeat it. ITER will only prototype the creation of tritium by the neutrons generated by the reaction. We have what we call tritium breeding modules that will test various technologies, by the way. We have to test. But, and we will use tritium, effectively. We will purchase tritium. But this is not to be confused with the reactor, because the reactor itself, we know this story. We have not enough tritium for fusion. We know this for a long time. It's even ridiculous. I mean, you cannot have a fission reactor operating just to feed a fusion reactor. This is absurd. So the challenge, and this is part of the ITER program and of the development of fusion, is to generate the tritium in situ with a sufficiently high tritium breeding ratio so that every neutron is creating 1.1, 1.2 tritium, so that we can really have let's say, a converging and sustainable system. So this is under development. So this kind of things is just confusing ITER and the reactor.
Yes, right. And there are a couple of questions that talk about the basically the effective energy out from ITER. So I think that you let's see. So one question is total full operation. Some reports say consume 350 to 450 megawatts for heating the plasma, cooling the coils, vacuum inverters, etc. That means your conversion of fusion power is 50%, and then how do you get a gain of 2 to 3 for ITER?
But again, here you have to be careful. ITER has no goal here. So even we don't have the right figures, but in any case, you have to be careful that in order to go for a gain and for a reactor, in fact, what counts is not the ratio of power, it's the ratio of energy, because you want this to happen on long time. So ITER will only operate with pulses, even though those pulses are several hundreds of seconds or even 1,000 seconds. But there was no interest to recover this energy and to do whatever with it. So when I say 2 to 3, it's even very difficult to compute what I'm telling you, because it will be an instantaneous capital Q. So these 300 to 400 megawatts are the power that you need for starting the plasma. This is wrong. I don't think you need at all 400 megawatts for the heating, cooling, and vacuum inverter. This is wrong. You need a very strong starting power just to break the plasma and to make it work. After that, you are not there. But never mind, because as I said, the question is not the ratio of megawatts; it's the ratio of megajoules that you will use and create. And so this question has only a meaning for the reactor. And all these people are right in saying that only the technologies and the solutions we have been putting in place for ITER are not sufficient enough. We need to work on the efficiencies. We need to improve. As I mentioned, if we are able to lower down or to have higher temperature superconductors, we will gain a lot. We had no time to discuss the tokamak solution versus the stellarator, but if also we go to a stellarator solution, then you gain a lot in the global efficiency. So all this is the goal of the next STEP program. It's extremely difficult. You could also ask me the question of what is the cost of a megawatt of a kilowatt hour generated by ITER. I can't answer. It's the same problem as what is the cost of a Formula One versus everybody's car. It's something that is still not in the picture. All the projections that we have, there are some projections, some publications, show that we are in the right ballpark, but there is still a lot of effort to do in terms of technology concerning essentially the efficiency of the overall process.
Yes, I really like the way you point out Formula One as an analogy.
ITER is Formula One, clearly.
Yeah, and I guess that apropos of that, there's another question. Q&A. The DOE estimates the cost for ITER construction at $65 billion. How is this technology expected to be competitive with other energy technologies?
By the same kind of solution. Now, the question of the estimate of the cost of ITER is also something that is extremely difficult for us, not because we want to hide, but because it's almost impossible to know. the projection of the cost of ITER is always a ratio between whoever, one of the partners' expenses and versus its fraction. So US is sort of 9% of ITER. And so if they make the ratio between what they spend and this 9%, they go to 65 billion. If I do the same thing with Europe, I go to 25 billion. If I do the same thing with China, it's probably much cheaper. So it's the cost of ITER is also an ill-posed problem because ITER is procured in kind. Okay, so it's extremely difficult. So the best picture we have, because also Europe is half of the 45% of the ITER procurement, is probably the European figure, and the European figure is more around for 25 billion today. But okay, we can discuss everything because the cost of banana in Washington and in Beijing is not the same. It's extremely difficult to compare.
Right. Yes, I think that we're out of time for questions, but maybe just as a last point, what would be your advice to young researchers entering the field, or for entrepreneurs, or for the public? Do you have a piece of advice for young scientists?
Yeah, first of all, it's a return of experience. Fusion, and I think you will not dispute this, Nat. Fusion is one of those research area where you will never close, you will never do exhaust what you can do in fusion. That's absolutely a very nice place to do research, to do activities, because my personal trajectory, I started as a pure theoretician. This is where I met Nat on the Hamiltonian interaction between waves and particles. I end up as the head of the engineering of ITER. In the meantime, I've done experiment, I've done modeling, I've done project, I've done management. So, and I did maybe 1% of what I could do in this story. So it's a very wide field where you can express either your talent in terms of a scientist, an engineer on a very difficult problem, or also your talent of trying to englobe all the aspects, because the integration, fusion is essentially a problem of integrating an incredible number of physics and technology elements into something that works. So it's building a very sophisticated car, a very sophisticated Formula One. So it's very interesting. There is a lot of innovation at the same time. And last but not least, as I said, I mean, it's an intellectual environment that is up to today extremely international, extremely exciting, extremely motivating. So now we are on a problem that is very clearly one of the most difficult problems ever, is to really capture and master one reaction that today is only happening on the stars. So if we manage to do that, okay, it's an open door for really, it's a game changer in terms of the energy consumption of mankind. So it's something that deserves really the effort. I don't want to say that we succeeded yet, but today we are on the good path.
I guess it's because we haven't succeeded that it's of interest to young people to help.
Yeah, of course.
Alain, thank you for this wonderful conversation. I think that the two of us could probably go on for hours about many of the aspects of the things that you raised today and many of the things that you didn't raise today. But I think that we're out of time over here. And let me just congratulate you again on a wonderful book and just a wonderful way of expressing yourself and describing the field and prophesying also about the future. It's just great. Great to talk to you.
Thank you, Nat. It was also a real pleasure to have you, to have this conversation with you. And it's also time to thank all our auditors and audience for their attention. I'm available for whatever questions. I mean, it's alain.bécoulet@iter.org. You can write me, you can raise questions. We can continue the discussion as long as you wish. It's a pleasure for me.
Great. Well, Thank you both so much for this fantastic presentation. And thanks to all of you out there for spending part of your afternoon with us. Please learn more about this book and purchase your copy of Star Power at harvard.com. On behalf of Harvard Bookstore, the Harvard Division of Science, and the Harvard Library, all here in Cambridge, Massachusetts, enjoy the rest of your day, keep reading, and be well. Thank you both for this tremendous conversation. This has been a pleasure.
Thank you, and good afternoon to all. Thank you very much.
Okay.